Okay, so this is the recorded video for the makeup lecture on March 17th. We missed the recording. Okay, so we're going to study the chapter 17. And we're going to start on the titration problems. So we will study the titration of weak acid with a strong base. And we're going to see the 4 typical stage. And depend on the stage of those titrations, and we can use different approach to calculate the pH. So we're going to use one example and to show the calculations for all the 4 stages. Okay, so we'll start here. The first stage is the first stage is finding pH before adding of any strong base. Second stage is finding pH after addition of some strong base, but before the equivalent point. The third stage is finding pH at equivalent point. The fourth stage is finding pH after equivalent point. The example we use is titrate 40.0 milliliter of 0.025 molar of benzoic acid, which has a formula C6H5COOH, with a Ka equals 6.3 times 10 to the negative 5, with 0.050 molar NaOH. So this is our example. And the first stage is finding pH before addition of any strong base. So before adding any strong base, NaOH or some other strong base, there is only weak acid in the solution. Thus, to finding pH for weak acid using the IC table. We first write the ionization reaction of our weak acid in water. Then we make the IC table. We know the initial concentration of our weak acid is 0.0250. The initial concentration of H3O plus is approximately 0 because some of those H3O plus come from water auto-ionization. And then this benzoate, our conjugate weak base, has initial concentration 0. So we know if the product has 0 concentration at beginning, so therefore at the beginning, our equilibrium shifting from left to right. So on the left, those reactant concentration are going to decrease, so therefore the change will be negative. Negative how much? And we will see the coefficient. So the coefficient usually, if they are 1, they are omitted. Okay, so those are the so-called coefficient. The coefficient will tell you how much change. So when you see a 1, you just see 1x. So whether they are negative 1x, positive 1x, depend on whether they are reactant or product. So this is negative 1x, and this will be the plus 1x, and this will be the plus 1x. So once we know the initial concentration and the change, we can just get the concentration at equilibrium. So therefore, for our benzoic acid, it will be 0.0250 minus x. For H3O plus will be x. For this C6H5COO1 negative is also x. So once we finish the IC table, we can write up our equation for our Ka. So this equilibrium, we can also write Ka here. So Ka is kind of the typical equilibrium expression for equilibrium. You write the products on the top, rectangle at the bottom. So our products, we have two products. One is H3O plus, the other one is C6H5COO, one negative. So we use angle bracket to represent the molar concentration. So we have rectangle C6H5COOH angle bracket. So next we will substitute those information we know into this equation for the Ka. We know the number for our Ka is 6.3 times 10 to the negative 5. So therefore we substitute this Ka by this number. And then we know the H3O plus concentration at equilibrium is X. So we write X for H3O plus. Then for the C6H5COO, one negative is also X. So then for our reactant, the benzoic acid, we have 0.0250 minus X. So next, we will solve this equation for X. Okay, so far we have our quadratic equation 6.3 times 10 to the negative 5 equals X squared divided by 0.0250 minus X. So we always try to solve the equation as simple as possible. Try to solve this quadratic equation. Use our typical approximation. Use the so-called small x approximation. So to do that, we need this condition to be true. We need 100 times the Ka if we solve a problem for weak acid, or if we solve a problem for weak base, will be 100 times Kb. So that should be smaller than the C0. So C0 is the initial concentration for the weak acid or weak base. So let's check that. So we take 100 times our Ka is 6.3 times 10 to the negative 5. And then we compare with our C0, which is 0.025. Is that small or larger? Well, let's say 100 times 6.3, so that become 6.3 times 10 to the negative 3. So that can be written as 0.0063, and that is true. So that's smaller than 0.0250. So therefore, we can use approximation. Let me abbreviate. We can use approximation. So that means the initial quadratic equation can be written as this. So let me copy the initial quadratic equation. So that when we use a small x approximation, so 0.0250 minus x equals or become this, because we dropped. X. Because x is so small compared with 0.0250. So therefore, the equation become simplified. So 6.3 times 10 to the negative 5 equals x squared over 0.0250. Okay, to solve this equation, we just multiply 0.0250 on the right and also on the left. I will just write here, so times 0.0250. So what happened on the right? So these two cancel out. So therefore, On the left, we still have our Ka, which is 6.3 times 10 to the negative 5. Then we also have this 0.0250 because we multiply this on both sides. Now we have x squared. So therefore, we take the square root of both sides. So 6.3 times 10 to the negative 5, and then times 0.0250 under the square root equals x. Okay, so you use your calculator, find out x equals 0.001255. Okay, so now let's go back to the IC table, see what is x. So you see here, x is the concentration of H3O at equilibrium. So therefore, we can just say x and H3O. So therefore, we can say we find out the concentration of H3O plus at equilibrium is x. So we write here H3O plus concentration at equilibrium equal to x equals 0.001255. Now the problem is you want to find out pH. So let me say pH equals negative log H3O plus molarity. Okay, so plug the number in. Our number for H3O plus concentration is 0.001255. Use calculator, you find out the pH is 2.901. Okay, so therefore, before the addition of any strong base, we have our pH for our weak acid is 2.901. The second stage is finding pH after the addition of some strong base, but before the equivalent point. We still have the same example, so we titrate 40.0 milliliter of 0.0250 molar benzoic acid. When you see this capital M, sometimes I read this as molar, which means molarity. So that's usually chemists to say those concentrations. And so you want to first calculate the equivalent point, and then we can know if we add in 10 milliliter of this 0.050 molar NaOH, is that before the equivalent or after equivalent point? So therefore, let's say to calculate or to find equivalent point or volume, we follow the following procedures. So first, write up the balance equation between the acid and the base. So we take NaOH plus C6H5COOH, produce C6H5COO Na, then plus water. So we first calculate the mole of the acid or the base, whoever has both the volume and the concentration given. And in this problem, the volume of the acid and also the concentration of the acid are given. So let's find out the moles of the acid first. We were converting the given milliliter of the benzoic acid, 40.0 ml, into the liters by using this conversion fraction. And then we will use the given concentrations to find out the moles. You're always using, whenever you're using conversion fraction, always checking the cancellation of the unit. So milliliter cancel out, then liter cancel out. So we have this mole left over, not canceled out. So that we have this much more of benzoic acid initially in the solution. And the next step, so once we keep this equation balanced, and then we have those coefficients. So later on, we use the coefficient to the conversions. Okay, so this one, this one, this one, this one here are the so-called coefficient. It's kind of a Molar ratio coefficient, and we use them to do the conversions. So converting more of the benzoic acid to more of NaOH. So from the last slide, we find out initially before the titration, we have 0.00100 moles of benzoic acid. Formula is C6H5 COOH. The name for this is the benzoic acid. So we are using this 1:1 ratio to convert. So let's see where are the 1 and 1 come from. So this 1 for NaOH come from the coefficient for NaOH. So then the 1 for the benzoic acid is also the coefficient for the benzoic acid. So therefore we have this much more of NaOH. So next step, you can use the molar concentration of NaOH, and then using this mole of NaOH here to find out the volume of NaOH. So you first get the liters. You see the concentration moles come out. Then we're using this conversion fraction 1,000 over 1 to get the volume in milliliters. So therefore, we have a 20.0 milliliter of NaOH. And this is the equivalent volume. So equivalent volume for this titration program is 20.0 milliliters. So therefore, adding 10.0 milliliter NaOH is before the equivalent point. And the pH calculation will be for a buffer system. Why that? Because when you have this much more of weak acid, and you only adding some of those strong base, not enough to reaching the equilibrium, reaching the equivalent point yet. So therefore, there are still some of those benzoic acid left over, and so therefore you have acid left over. Then in the same time, we produce some of those conjugate weak base. So therefore, in our mixture after we titrating, we have both the weak acid and weak base. So this will be a buffer. So therefore, to find the pH after adding some NaOH, but before the equilibrium point to a buffer calculation. So therefore, we first have to find out what is the concentration of the acid written in red, and then this will be the base. So we need both information, either using the IC table or the Henderson-Hansbrock equation. So to do that, we have to write the equation between the NaOH and then this benzoic acid. So then we will calculate the initial moles of the acid and then the added on moles of the strong base. So the initial mole of the weak acid, as we calculated before, but we can do here again, is using the given volume, converting the volume into from the milliliters into liters, and then we are using the concentration so to convert into moles. Okay, so the next fraction will be this fraction that comes from the molar concentration of the benzoic acid. So ml comes out, L comes out. We get multiply, and we see how much initial mole of the weak acid, which is 0.00100 moles. So next, do a similar approach, calculate how much moles of the added strong base. So the volume we added is 10.0 milliliter. So using the same conversion fraction, 1 liter equals 1,000 milliliter. And then next, we also use the molar concentration for the NaOH, which is 0.050 moles. So therefore, we get 0.00050 moles. Okay, so next, we will calculate the moles after reaction between the weak acid and the weak base added, which easier to use the table format. So this table is a little bit different than the IC table for the equilibrium, because this equation is not an equilibrium. So let's do that. Summarize the information. So how much NaOH before the reaction, which means before this reaction happens, and obviously the NaOH already added to the solution, to the mixture. So we see this is 0.00050 moles. Initially, how much benzoic acid we have? We have 0.00100 moles. Initially, we don't have any moles of the conjugate base. Water doesn't matter because water is the solvent. Water is solvent and has a lot of water, so we don't worry about that. So next, we want to find out who is the limiting reactant. Because limiting reactant will be the reactant that used up. So that depends on how much we have for the reactant, and then depend on the coefficient. So let's emphasize the coefficient again. If you don't see any number, that means they are 1. So the coefficient is an integer number. So usually the integer number 1. So therefore, the coefficient ratio or the mole ratios between these two reactants are 1 to 1. So therefore, to find out the limiting reactant, we just compare which reactant has less amount. Turn out in this problem, NaOH has less. So therefore, this will be our limiting reactant. So this NaOH is the limiting reactant. So therefore, the change will be negative of this amount of our limiting reactant at the beginning, and then you also see 1-to-1 ratio, and this is also reactant. So therefore, this also negative, and negative also this much. So then this is the product. So therefore, this will be the plus. Okay, so once we know the initial, the change, and we know the after. So after reaction, this NaOH become 0, the benzoic acid become, you just subtracting these two numbers, become that. The conjugate base, so this guy is our base for the buffer, and this is the acid for the buffer. So obviously 0 plus the change, so therefore just 0.00050. Okay, now we know everything in the mixture solution. So we have 0 NaOH left over, but we have some weak acid left over. We also produce some of those weak base. So therefore, we see the information on the top, and we just can using those information, either using Henderson-Hansenbach or the IC table. So we can use Henderson-Hansenbach, as I told you, to make our problem a little simpler. Whenever we have a buffer problem, so for our class, whenever there is a buffer pH problem, we can safely use the Henderson Hansel-Brock equation, which is written as pH equals pKa plus log, the concentration, the molar concentration of the base divided by the molar concentration of the acid. All right. So to calculate the molar concentration, we need to know the total volume. But I will show you for buffer program, you can use more ratio instead of molar concentration ratio because the volume will cancel out. So in this example, let's say that. So our total volume of our buffer, just all together, all the volume, so equals 40 benzoic acid plus 10 of the added base. We have 50.0 ml total volume, and that equals 0.050 L liters. So therefore, this base concentration, our base will be the C6H5COO1 negative equals this guy. The Na is spectator, so doesn't matter. So we have 0.000500 divided by 0.050. I will keep right this way, and then you will see later on the count out. So our acid, similar approach, because acid also have this much more, and also in the same volume. That's also more and liter. So now we plug those into the equation, into the Henderson-Hansel-Brock. So pH equal to pKa. We'll find the pKa later. So equals log. The concentration of the base on the top, so 0.000500. Our omitting the unit, which divided by the 0.050. Okay, so this is the molarity of the base. Just having this problem, they all have the same number. So for the acid, it's 0.000500, also divided by 0.050. What I want to say, the calculation, to save some time in the calculation, is this guy. So this volume comes out. So therefore, when you use the Henderson-Hansel-Brock equation, so you can skip when use the H equation. We can skip the calculation of the molarities. When we use HH, we'll skip this step. So instead, we'll take this number as a molarity for the base, take this number as a molarity for the acid, because later the volume comes out. Okay, now we'll finish the calculation. So we see this is Ka. So therefore, pKa equals negative log of Ka. You plug those numbers in, so you have negative log 6.3 times 10 to the negative 5. That will give us 4.201. So therefore, we'll put here 4.201. Then this guy, everything comes out, become log 1. So log 1 is 0. So therefore, plus 0. So therefore, our final answer is 4.201. So that's the pH. After we adding 10 milliliter of NaOH, so that is before the equivalent point, and we did a buffer calculation. We found out our pH is 4.201. Okay, so the third stage is at equivalent point, and we still have the same titration example. So you also practice this type of problem in the practice question for Chapter 17, question number 9. So from the part 2 of this question, we found the equivalent volume is 20.00 milliliter NaOH. So to do the calculation for the pH at the equivalent point, we also have to find out at this stage what level over in the reaction mixture. So we'll use our typical approach to find out the moles of the acid, the more of the initial acid, and more of the added base. So we did that quite a few times. We start with the given 40.0 milliliter using our 1 liter equals 1,000 milliliter, converting volume into liters, and we use molarity. Molarity can be written as a fraction. So therefore, we have this second fraction here. We check the cancellation of the unit. So therefore, we have 0.00100 moles of the initial weak acid. And then we see how much base do we add. Because this is at the equivalent point, we see at the equivalent point, we need this much a milliliter of NaOH. So therefore, we start with 20.0 milliliter, and then using the same conversion between liter and milliliters. So therefore, we will get the volume in liters first, and then we use the molarity of NaOH, which is more concentrated than the acid, is 0.0500. So the similar cancellation, and we have the same amount of the added on strong base. Okay, so it looks like they are going to all used up. So that's good, but even they use up, we'll have something new in the solution. So therefore, we write our reaction between the base and acid. So we have this equation. Then we will use our before change after. So before we have 0.00100 more of NaOH, 0.00100 more of the benzoic acid, 0 more for that, what doesn't matter. So then the question is, who is the limiting reactant? So again, I emphasize this table is not IC table. IC table that E setting for equilibrium, but this reaction is not an equilibrium. It's one-way reaction. So therefore, we don't worry about how much product we produce. We always want to use up all those reactants. So therefore, the reactant will be the one that use up. Well, you have to say like how much of those reactants we have, then what are the coefficients? Because the coefficient will tell us the reaction ratio between them. It just turns out for this question, they all have one coefficient, and one. So therefore, both of them are limiting reactants. So this is limiting reactant, and this is also limiting reactant. So they're both used up. So therefore, the change for both of them are the same. So therefore, we will produce the same amount, same moles of the conjugate base. So after reaction becomes 0, then this becomes 0.00100. All right. So now, what do we have in our reaction mixture now? We don't have any of those strong base. We don't have any of those weak acid. We have some of those conjugate weak base. So then you cannot assuming our pH will be neutral because we have our conjugate weak base. So we have to find out what is the concentration of the conjugate weak base, then use IC table to calculating the pH for a weak base. So the total volume so far we have is 40 plus 20, 60 milliliters, so that it becomes 0.0600 liters. And so therefore the concentration for the for this conjugate base, so this is our base, equals this, because this is the compound, but the Na is spectator ion in the neutral. So what is really the base? It comes from this product. So therefore we write there. So we find out more for this guy. So therefore this more of this equals more of our, so this more equals more of the C6H5COO1 negative, which is really the matters, but this is what our weak base. So now we find out our weak base concentration. Yes, our weak base concentration is this model. So next we'll use IC table. So the typical approach. So we'll have this equilibrium. So this equilibrium has a KB. So we have to find a KB by using Ka. So before that, we probably first finish this IC table. So we see this will be as this condition indicated as the initial condition indicating. So our equilibrium was shifting from left to right. So therefore, the concentration here will be change will be negative. The concentration here for the product will plus and plus. So plus how much depends on the coefficient. So if you have coefficient 1, you will have 1x. So either negative 1x or plus 1x. So they all have a coefficient 1. So therefore, they all have x. So therefore, this reactant at equilibrium will be the initial concentration minus the change. And this will become x and x. All right. So next, we will just go find out what is our KB, and then we'll substitute our KB and then those numbers into this KB equations. So to find KB, we will use the equation for Ka, to find KB is Ka times KB equals Kw. So Kw is a constant. Kw is a constant. And we know this constant at 25 degrees Celsius is this number. So we usually assume our temperature is 25 degrees Celsius. Okay, so by using this step, we find out the KB. So therefore, next you are substituting those numbers into our equation for KB. So therefore, we have 1.587 times 10 to the negative 10 equals x times x divided by 0.01667 minus x. Right, you can solve this equation with a quadratic formula or calculator or some technique, but we will use our small x approximation, which is okay because 100 times our KB. So remember before we using this 100 times KB less than C0. So if this is true, we can use in this approximation. You see 100 times 1.587 times 10 to the negative 10 equals 1.587 times 10 to the negative 8. So I would say this is much, much smaller than 0.01667. So therefore, what we did is drop this guy. So therefore the equation becomes simple. So let me erase all what I write. So using this small x approximation, this becomes x squared over 0.01667. So if we multiply this 0.01667 here, and also multiply 0.01667 there, so these two cancel out. Then we take the square root, so therefore we have this equation here. Then we take the square root, we get this number. So then you look back into the IC table, see what is the X. So here the IC table. So this is X, and this is under the hydroxide. So therefore, this X not really the H3O plus or H plus. So it's hydroxide. So therefore, we find out hydroxide concentration equal to X. So we take the negative concentration, negative log of the concentration of hydroxide, we get pOH. So we get pOH 5.789. And then you know the equation is pH plus pOH equals 14. Therefore, we finally find this number pH at equivalent point, which is as what we predicted before, not 7, because we get a conjugate weak base. Okay, so the fourth stage is finding pH after equivalent point. So we know the equivalent point for this problem is 20.0 milliliter of NaOH. So we add in 25. So therefore it's after. So that's it after equivalent point. So the equivalent point is 20. So if you're adding anything more than 20, it's after. So then we were using our approach is to find our initial mole of acid. So we have 40, and with the conversion between liter and the milliliters. So our concentration for the weak acid is 0.0250. So those cancel out. So we remember we have this much moles of weak acid. So similarly, you see, do a calculation for the added strong base. We add 25.0 ml. So we use a same fraction, but the concentration are different. That's 1 liter, 0.050 moles. So our concentration, milliliter, liter cancel out. And then what we get, so that will become 0.00125 moles. Now we'll use our tables before, after, before change and after table. So before we have 0.00125, 0.00100, 0 here, 0 here. So now again, with the limiting reactant, with our LR. So again, that depends on how much we have and what are the coefficient. So they all have a coefficient of 1, 1, 1, and 1. How much they have? The last one will be the limiting reactant. So therefore, this will be our limiting reactant. So therefore, the change will be the initial amount of the limiting reactant. Initial amount, initial mole of the limiting reactant. So then for the product, so that's also 1:1 ratio, that's plus that much. So therefore, at equilibrium, after equilibrium, this become 0.00100, this becomes 0, and then this becomes 0.00025. Okay, so what do we have now after this, after adding 25 ml of the NaOH? We don't have any weak acid anymore. We have some of the conjugate weak base, and we have the strong base. Okay, so for most of the problem, we don't have to consider those pH effect from the conjugate weak base. Therefore, we just concentrate on this strong base. So for most of the problem, that's okay. So let's say this is our strong base, and this is our how much our weak base. So to do that calculation for the strong base, you just see how much more left over. So we have this amount more. Then you just see what are the total volume. So total volume is 40 plus 25, 65. 65 is 0.065 liters. So therefore, take the mole divided by liter, get the concentration of the leftover, and AOH. Okay? That dominates. So this strong base dominates our pH of the solution. And once you get the molarity of the strong base, take the negative log, get the pH, then 14 minus pH. So that is a pH after equivalent. After equivalent point. All right, so that is the typical 4 stages of titrating a weak acid with a strong base. And we'll summarize those information on the next slide. So we have those examples in the previous slide in this lecture. So the first stage is finding pH before addition of any strong base. So we did a weak acid pH calculation with IC table. So the second stage is finding the pH after addition of some strong acid, but before the equivalent point. We did a buffer calculation with Henderson-Hansel-Bach equation, or if you want, you can also use IC table, but using the H equation much simpler. Third stage is finding pH at equivalent point. We did a conjugate weak base pH calculation with the IC table and with the Kb. So Kb will equals Kw divided by the Ka of the conjugate acid of that weak base. So the fourth stage is finding pH after equivalent point. We did that by finding the leftover strong base concentrations. Then we take the pOH, then we get a pH. So that's of the 4 stages. So next section, or before the next section, let's say when we titrating a weak acid with strong base, we will have our typical titration curve as shown in this picture. So that will be similar as this week's lab. So what this statement tells you is if you have a titration pH curve like that, you identify what is the equivalent point. So in this example, so this is 10 is our equivalent point. And so then by this statement, which means the pH at half equivalent point. So 10 is the equivalent point, and half of 10 is 5. So you locate 5 ml, so that will call the half equivalent point. You go up to the curve, you get a point, and go to the left, you find the pH. So it's about 4.8 or 4.9. So then that means for this weak acid, so that equals our pKa. Why that? Because let's see from the Henderson-Hansel-Bach equation. So Henderson-Hansel-Bach equation tell you pH equal to pKa plus log base over acid. Okay. So then at half equivalent point, the base concentration equals acid concentration. Okay. So therefore, this can be simplified. So your pH will equal to pK plus log and base concentration are the same, so that become 1. Therefore, become pKa plus 0. So that's why at half of the equilibrium point, pH equal to pKa. You can also titrate some of those polyprotic weak acid. And also, let's see, before we do that, we compare the titration of a strong acid with strong base and weak acid with a strong base. So the bottom line here is our strong acid, and here is the strong base. So that means we're titrating acid with base. So all those titration of those different acids, we use our strong base. But some of those acids is strong, and some of those acids are weak. So only this one is strong acid, and all the others. So let me see this one, this one, this one. So all the other 4, so they are weak acid. So what is the difference between the titration pH curve? One is a solution of weak acid has a higher initial pH than the strong acid. So that is true. So the initial pH, so that for the strong acid, which is lower, then those guy are the initial pH. So they are the initial pH for the WA, which means weak acid. Okay, another point is pH change near the equivalent point is smaller for a weak acid. That is at least partially due to the buffer region. Remember we did one calculation. So before the equivalent point, so your solution really turns into buffer. What that means is, let's see how much of the pH change. Let's see for the strong acid, the strong base. So this is strong acid, and you have this much pH change. So this is the pH change for the SA, for strong acid. For weak acid, let's see, one weak acid, let's see this green line here. So this acid here, this acid. So that's the pH change for WA, for weak acid. And obviously this change here for this weak acid is much smaller than the pH change for a strong acid. Okay, so the last point is, so let me erase all those. And what the last point is, the pH at the equivalent point is greater than 7 for the weak acid. So this pH, so this is the equivalent point, let's see, for SA, for strong acid. And obviously all the other points is for, so those are the equivalent points for WA, for weak acid. So this, for the strong acid, is approximately 7. So therefore, for the weak acid, your equivalent point pH is greater or more than 7. Because what happens is you produce a conjugate weak base. So therefore, a basic solution will have a pH higher than 7. Okay, now we see this is the titration of a polyprotic acid. So in this example, we can see there are, so this is H, that's H. And these are the ionizable H. So therefore, this is a diprotic acid. So therefore, we have 2 equivalent points. The first equivalent point is 50. So they were taken one H at one time. So therefore, we have a different equivalent point. the first equivalent point is taking the first H. The second equivalent point is taking the second H. You can also find out the pKa for taking the first one, first H. You can also find the pKa for taking away the second H by using same approach. So if the first equivalent point, so this will be the equivalent point, or we say this is the first. So here this is the first, it's 50. So using our approach, so the pH at half equivalent will be the pKa. So half of 50 is 25. So therefore this will be the pKa1. So for this sample, you probably get about 1.6 equals pKa1. And then the second equivalent point, so our second equivalent point here is 100 second equivalent point is 100 ml. So the half second equivalent point is halfway between 50 and 100, which means halfway between the first equivalent and the second equivalent. So therefore, the volume for this second will be this here point here, which is 75 ml. So that's the volume. You want to find the pH, you go to the left, you get this point here. So here about 7, so you get about 6.5 equals pKa2. So next section about the solubility equilibrium. Okay, we learned some of those ionic compounds is soluble, some are insoluble in CHM-116. But here we will have a little bit different concept. Even some of those compounds, as we see before, is insoluble, but they are not 100% insoluble, so they still have a small amount of ions get into water. So this section about if that happens, because they are ionic compound, they will totally dissociate into ions, and that kind of become an equilibrium situation. So what you do, you will write up those equilibrium equation, then you write up the equilibrium constant expression, and then this equilibrium constant expression will have a special name called the KSP. So S for solubility, P for product. So for example, when you have barium sulfate, so barium sulfate, as we learned in CHM-113, is insoluble. So therefore, you are expecting those kind of problem called the KSP or the equilibrium constant of a very, very small number, but they are not really that much soluble. So the equilibrium constant expression will be the typical expression for the equilibrium constant, the product over the reactant and the coefficient as the exponent. So in this example, we don't have that barium sulfate in this expression because you can think about barium sulfate solid concentration equals 1. Not exactly equal to 1. Just 1 just symbolize the concentration does not change. So actually really that's concentration is constant. Right. So don't make sure you don't including those something in your chemical reaction that is solid or liquid in the expression for your K, whatever the K. So now the example is you have barium phosphate. So in this example, you will have those coefficients, not 1. So these 3 will come from this subscript, and then these 2 come from that subscript. So once you know those coefficients, and when you write the equation for the KSP, so make sure you will use those coefficients as exponent. So 3 exponent, or called power, it comes from the coefficient for that species. So that similarly, if you have a coefficient that is 2, and you will use 2 as the exponent for that ion. All right, so you have to keep in mind KSP is not the same as solubility. Solubility here in CHM-116 referring to the quantity of a substance that dissolve to form a saturated solution. So commonly used unit for solubility is a gram per liter or mole per liter. So mole per liter, as you familiar with, is our molarities or molar concentrations. So when we have those numbers for the KSP, which means you need to do your calculation using molarities. So after you get in molarity, the molar solubilities, then you can convert into gram per liters or some other unit. Okay, so this question is which of the following expression correctly express the solubility product for the Ag3PO4? So you probably want to write out the equation, especially the first time. And you write Ag3PO4, just take one of this, just one, which means coefficient here will be 1. So you will write, actually you should write really long arrow pointing to the left, really small arrow pointing to the right. That means you don't have too much going on to the right. So not that much soluble. So this will have the KSP. KSP is much smaller than 1. So as they dissolve, they will dissociate. So they will produce ion. You have to remember some of those common charge for the ion. So for Ag will be 1 plus. For PO4 together, so don't separate P and O. You keep it right, P and O, PO4 together is 3 negative. Then the state is aqueous. So then the coefficient here will be 3. So this 3 come from that 3, come from this subscript 3 here. So that's how we get the 3. So then the plus 1 charge, 3 negative charge, kind of memory. Right, so therefore, once you have the equation, and you want to write the equation or the expression for the KSP, so product on the top, angle bracket, so it's angle bracket closed, which means molarity. So then use the coefficient as exponent. Then another molarity for the other product. Then let me show you why we don't have that in the equation. But initially you put write that as Ag3 and PO4S. Then you see that is 1. So therefore that disappeared. Because Ag3 PO4S angle bracket equals 1. So therefore our final answer for the KSP or equals Ag plus to the third power, then PO4 3 negative to the first power. So therefore the answer is C. Okay, for this question, we are going to really do a calculation because we are given the KSP. You can see KSP is really small number, 10 to the negative 11. Then ask us what is the molar solubility. So that means much moles of CF2 dissolved or can dissolve in 1 liter solution at 25 degrees Celsius. So that's what I mean by the molar solubility of compound. Just ask you to calculate what is the molar concentration of this guy together dissolve. So as soon as this guy dissolve, because it's ionic, it will dissociate into ions. So therefore, you want to first write out your dissociation equation or equilibrium equation. So these two come from this subscript. So once you have that, you write out your equation for the KSP, and then you have this equation. So next, you will use your typical IC table. So you can see here. So if you write this as the equilibrium, so this is equilibrium, and then you see here the 2, and then here the coefficient. That's why the other coefficient is 1. So therefore, the other guys has 1x. Yeah, even though this doesn't matter, but this still you will see this is how much it dissolve. So this guy is 1x, then is 2x. So next, you just substitute those x into this equation. Okay. So we will substitute this x here, this 2x here. So what you get is this. Just little details, how you get that from that. Well, you know that x times 2x squared, which means you will square both of them separately. Okay, you square the 2, you square the x. So that becomes x times 4x squared. That becomes 4 times x cubic. Right. So initially you get 3.9 times 10 to the 11 equals 4x cubic. So you divide by 4, you divide by 4 on both sides, 4 and 4 come out. So you get some equation like this. Then you just take the cubic root. Right. So cubic root in your calculator, you might find the cubic root, or you might doing that. Okay, so 3.9 times 10 to the negative 11 divided by 4. You can write this as to the power 1 over 3. So that equals x. And use your calculator, you find x, this number. Right? So then x will be our molar solubility. And if you want to convert this molar solubility into like gram per liters, so you can use molar mass. So the molar mass for that CAF2 will equals approximately 40 plus 2 times 20, about 80 gram per mole. Okay, so you take 80 gram per mole times this, so you get this, about this much gram per liter. All right, so this is the makeup video for the lecture, what we're supposed to do on March the 17th, but I did not get the record, and that's it.